Hey there, and welcome to This Explainer. Have you ever stared at a green circuit board and just wondered how those tiny, random-looking metal and ceramic shapes actually make your computer, your phone, or your car function? Well, you are definitely in the right place. Today, we're completely decoding that hidden language of hardware, unpacking the fundamental building blocks of all electronic circuits.
Okay, so here's our roadmap for today. We'll start with the fundamental building blocks, then move into passive components explained, dive into active components uncovered, and wrap up with interfacing and protecting circuits.
Let's jump right into part 1, the fundamental building blocks.
Basically, everything on a circuit board falls into one of two major camps. It's kind of like the ultimate showdown in electronics, passive components versus active components. Think of passive components as your pipes and valves. They can store, dissipate, or resist the flow, but they absolutely cannot introduce net energy into the circuit. They rely entirely on the electrical energy that's already there. Active components, on the other hand, well, they're your pumps. They require an external power source to literally inject power into a circuit, amplify signals, and actively control the flow of electricity.
Which brings us nicely to part 2, passive components explained.
Let's start with the true unsung heroes that keep the electrical environment balanced, starting with the resistor. This little guy is your primary tool for restricting and regulating electrical flow. Imagine putting a kink in a garden hose. By squeezing that hose, you limit the water pressure, right? A resistor does exactly this for electricity. It drops voltages and sets safe operating levels so that the really delicate components further down the line don't just get blown out by too much power.
And what's really cool is how versatile this basic concept is. You've got fixed resistors that just hold a steady, predetermined value, measured in ohms, by the way. But then you have variable resistors, like the physical volume knob on a stereo, which you can adjust manually. We also have these clever little environmental sensors. Thermistors change their resistance based on temperature, and light-dependent resistors, or LDRs, change based on light. That's literally how your phone knows to dim its screen when you walk into a dark room.
Next up, we have the capacitor. Now, if a resistor restricts flow, a capacitor is more like a rapid response storage tank. It actually blocks direct current while storing alternating current energy using an electrostatic field. It fills up with electrical energy and can dump it out extremely quickly. They are absolutely incredible for timing applications and for filtering out unwanted noise in a signal. And you'll generally see two main types. Ceramic capacitors handle high frequencies. They have pretty small capacities, but they react instantly. On the flip side, you've got electrolytic capacitors, which are polarized, meaning they have strict positive and negative terminals. These act as massive buffers. So if the power supply from your wall outlet stutters for even a fraction of a second, an electrolytic capacitor discharges to fill the gap so your whole computer doesn't crash. Now, unlike capacitors, which use electrostatic fields, inductors take a totally different approach. They're basically coils of wire that store energy in a magnetic field, and they exist to resist any sudden changes in the current flow. Whenever current runs through a wire, it creates a small magnetic field, right? Well, by coiling the wire, an inductor amplifies that field. So when current tries to suddenly spike or drop, that magnetic field actually pushes back, smoothing out the flow.
And if you place two inductors really close to one another, you get a transformer. These step AC voltage up or down using magnetic cores. And the wild part is they do this without changing the actual frequency of the electricity. Energy from one coil just jumps to the other through electromagnetic induction. This is exactly how the thousands of volts from the power lines outside your house are safely stepped down to the 120 or 240 volts that actually come out of your wall sockets.
So, okay, we figured out how to tame the energy using those passive components. But that leaves us with a pretty massive question. How do we actively drive, amplify, and process these signals to actually compute information, or, say, power motors?
Let's dive into part 3 to find out. Active components uncovered.
These are the absolute backbone of modern electronics because they use an external power source to inject and manipulate signals. Starting with the diode, think of it quite literally as a one-way valve for electricity. If you accidentally put batteries into a device backward, the reason your device doesn't immediately fry is usually because a diode is standing guard in there, blocking that reverse current from destroying the delicate circuitry. And diodes wear a few different really fascinating hats. You've got rectifiers, which convert alternating current into direct current just by chopping off the negative half of the AC cycle. Then there are Zener diodes. They act as a one-way valve until the pressure gets too high,
at which point they hit a specific breakdown voltage and safely allow current to flow backward. This is fantastic for regulating voltage. And, of course, light-emitting diodes, or LEDs. The screens and indicator lights we look at every single day, they're simply diodes that happen to release photons as current passes through them.
All right, now we arrive at what is arguably the single most important invention of the 20th century, the transistor. It acts as a microscopic switch or an amplifier. You apply a tiny, tiny electrical signal to one of its pins, and that tiny signal opens a gate, allowing a massive current to flow through its other pins. It literally allows electricity to control electricity, which is the foundational logic you need to build a computer. And they generally fall into two major families. You've got bipolar junction transistors, or BJTs, which are current-controlled and fantastic for amplifying analog signals. But then you have field effect transistors, specifically MOSFETs. These are voltage-controlled devices. They are incredibly efficient, generate way less heat, and switch on and off at absolute blinding speeds. Because of this, MOSFETs are the undisputed champions of digital processors.
What is truly mind-blowing, though, is the scale. We're talking millions, sometimes billions, of these tiny components packed onto a single sliver of silicon. When you hear about an Apple or Intel chip, you are essentially looking at an integrated circuit where all those resistors, capacitors, and primarily MOSFET transistors are etched together at a microscopic level. And these complex integrated circuits, or ICs, basically split into two camps. Analog ICs process continuous real-world signals. Things like operational amplifiers and audio amplifiers live here, taking the continuous wave of a voice recording and amplifying it perfectly for a speaker. Digital ICs, on the other hand, deal strictly in discrete ones and zeros, on or off. This is where your microcontrollers, microprocessors, and memory chips live, constantly flipping millions of microscopic transistors just to process your data.
Okay, so we have all these brilliant internal workings humming along. But how do these delicate circuits actually interact with the physical world? You know, like when a human finger presses a button. And for that matter, how do they protect themselves from sudden, catastrophic power surges?
That brings us to our final section, Part 4, Interfacing and Protecting Circuits.
To bridge the gap between the electrical domain and our physical world, we use a few key components. Switches are pretty straightforward. They mechanically interrupt or complete a circuit. But relays? Relays are incredibly clever. A relay is an electrically operated switch. Imagine a tiny, delicate microchip that needs to turn on a massive, high-voltage industrial motor. The chip obviously can't handle that voltage directly. Instead, it sends a tiny, safe signal to a relay. That small signal creates a magnetic field that physically pulls a heavy-duty mechanical switch closed, turning on the motor. It securely isolates the brains from the brawn.
Of course, to prevent catastrophic literal meltdowns, you need security guards. That's where fuses and circuit breakers come in. A fuse is actually designed to self-destruct. It contains a super thin wire that will intentionally melt and snap the circuit open if the current ever pushes past safe limits. You're sacrificing a 10-cent component to save a $1,000 motherboard. Circuit breakers do the exact same thing, but they can be mechanically reset after they trip, which is super convenient for household electrical systems.
It really is incredible when you step back and look at the big picture. All these individual, highly specialized tools, from a capacitor storing a quick electrostatic charge, to an inductor resisting a sudden spike, to a microscopic transistor switching millions of times a second, they all assemble in perfect harmony to create the modern world we rely on every single minute of the day.
So I want to leave you with this final thought to ponder. As you're watching this explainer right now, which of these fundamental building blocks is working the hardest to bring this information to your eyes? Is it the millions of transistors rendering the graphics? The LEDs illuminating your display? Or maybe the electrolytic capacitors making sure your power stays perfectly smooth? Thanks so much for exploring the amazing architecture of electronics with me.